What we have to understand, and I think some of us do, only the most delusional people in the oil industry don't get it, that we're moving toward the last of the oil era.
$100 million worth of oil going up in smoke every day.
We have several crises now, and they're all surrounded with oil. First, we have oil at $70 a barrel on world markets. Now, when I wrote The Hydrogen Economy, I predicted it would go to 50, and people said, oh, that's not possible. We're now at 70. Goldman Sachs predicts $100 a barrel. The International Monetary Fund says the price of oil is going to continue to go up for the next 25 years. Of course, what will happen on the 26th year? It's going to keep going up forever. Secondly, global warming. Global warming is the entropy bill for 200 years of the oil age. We've spewed so much carbon dioxide into the atmosphere, we can't get the heat off the Earth. And this is the first time human beings have actually affected the entire chemistry of the planet. It's the most impressive accomplishment of the human race. It's just a negative one. And then three, we've got the increasing problem of third world debt. You know, the young people say cancel third world debt at these world economic forums, and I say amen, but you have to know what the debt's from or it's going to come right back. The fact is, what's really killing the third world countries is the high price of oil. They can't afford it. And finally, the Middle East. We've got American troops and other troops stationed in the Middle East. One would have to be naive to believe there isn't an oil connection. We're positioning those troops there to protect this geopolitical interest. We're creating more terrorism as a result, and the world is becoming a much more geopolitical hotspot than it was. Imagine what it's going to be like in 10 years from now when we're all squabbling over less and less oil. We grow our food in oil, our plastics, our building material, our clothes, our transportation, heat. It's all about oil. So the oil crisis, global warming, third world debt, the geopolitical tensions in the Middle East, this is enough to suggest we need to get off oil. So then the question is, what do we do?
This was just the beginning. We escaped, but only into the clutches of the greatest storm in American history. And finally, the Earth disappeared from our view.
Tomorrow's energy, which is such a topical subject today, was already discussed in 1874 by visionary science fiction writer Jules Verne in his novel The Mysterious Island. Verne tells the story of several Union soldiers headed by Captain Cyrus Harding who escape from the Civil War aboard a hot air balloon and land on a strange wild island. The sudden privation of typical modern comforts forces the men to reflect upon the destiny of humanity. Discussing energy, the soldiers ask Captain Harding what will be used as fuel when coal runs out. Water, answers the captain to the incredulous soldiers. Yes, my friends, water, broken down by electricity into its primitive elements of oxygen and hydrogen, will be an inexhaustible source of energy. Water will be the coal of the future. Verne's island was a wild land with erupting volcanoes, impetuous waterfalls, and active geysers. More than a century later, on an island surprisingly similar to Verne's, a man nicknamed Professor Hydrogen is trying to turn Captain Harding's vision into reality.
I came to the University of Iceland in '62 when I had finished my study in Germany. And then I started a very extensive research work on our groundwater systems, especially the hot groundwater systems. After 50 years or so, we had got a pretty good picture of the size of this energy source. Then it was quite clear that at that time we were still importing 40% of the energy consumed. But we had only harnessed a very small fraction of our domestic energy sources. So it's natural to start thinking, can we use our domestic energy sources to produce fuel that could replace imported fossil? That's how it started.
Universally recognized as the pioneer of the hydrogen society concept, Professor Arnesen has been seeking to create a hydrogen economy since the 70s to end Iceland's dependence on imported fossil fuel.
At the beginning, we were considering various alternatives like methanol, synthetic gasoline, ammonia, but we have concentrated on hydrogen only after the breakthrough of the fuel cells.
But what exactly is and how does a fuel cell work? A fuel cell is an electrochemical energy conversion device that takes oxygen from the surrounding atmosphere and combines it with hydrogen to generate electricity and water. Hydrogen is the most abundant element in the universe. On Earth, it is mostly found chemically bound to other elements and can be extracted from many materials such as natural gas, methanol, coal, biomass, and water. We'll use a PEM proton exchange membrane fuel cell as an example. As hydrogen flows on the anode side, a platinum catalyst facilitates the separation of hydrogen gas into electrons and protons, hydrogen ions, in the PEM fuel cell. The hydrogen ions pass through the membrane at the center of the fuel cell and combine with oxygen and electrons on the cathode side to produce water. The electrons, which cannot pass through the membrane, flow through an external circuit containing an electric load that consumes the power generated by the cell. Fuel cells offer many advantages compared to heat engines, including high efficiency, virtually silent operation, and no polluting emissions. Invented by Sir William Robert Grove in 1839 and perfected by Francis Thomas Bacon between the 30s and the 70s, fuel cells were first used in the early 60s when NASA installed small alkaline units on its spacecraft. Thanks to significant developments in the late 80s and early 90s, fuel cells could be made smaller, more powerful, and cheaply enough to eventually replace conventional power technologies.
The fuel cells are obviously the power engines of the future, and hydrogen is obviously the cheapest fuel to make in the long term, and it's absolutely clean.
When Professor Arnesen first launched the idea of basing Iceland's economy on home-produced hydrogen, few people shared his vision. But once major corporations started visiting his laboratories to learn more about his ideas, Icelandic politicians changed their stance and formally decided to invest in hydrogen as the fuel of the future. In 1999, this growing interest led to the creation of Icelandic New Energy, with 51% of the shares owned by a consortium of Icelandic corporations in the energy sector, the government and the University of Iceland, and the remaining 49% owned by Daimler Chrysler, Norsk Hydro, and Shell. Professor Thorstein Sigfússon was appointed the head of Icelandic New Energy.
In 1997, the Minister of Industry and Trade formed a committee to explore the possibility of domestically produced fuels. And in the wake of the committee work, the government of Davíð Oddsson declared officially Iceland aiming for a hydrogen society.
I declare the hydrogen station open.
When Professor Sigfusson joined the International Partnership of Hydrogen Economy in the United States of America in 2003, Jon Born Skulason was appointed the new head of Icelandic New Energy.
So we are here in Iceland looking at the first commercial hydrogen filling station of the world. This station was opened on April 24th, 2003. It's a part of a European Union supported project which is called the Actos program. It involves 3 hydrogen fuel cell buses and a commercial filling station. This station is assembled as on-site production of hydrogen, meaning that we are connected to the electric and water network of the city of Reykjavik. So we produce the hydrogen on-site. It's a gaseous hydrogen. We compress the hydrogen on-site, and then we dispense the hydrogen directly from the dispenser on board the bus. And shortly we will see the bus arriving at this station, and it will be refueled here, just as a normal vehicle can be refueled. So now we are on board one of the hydrogen buses in service in Reykjavik. We have 3 hydrogen fuel cell buses running. They are all operating in just normal commercial service like any other diesel vehicle or any other bus. When Icelandic New Energy started, we looked at 3 potential stages. First of all, to have a bus operation going, then to see passenger vehicles coming onto the streets, and finally a marine application. The bus project was then more or less the first project we started with. We thought it would be important to have buses, mainly so that the vehicle and the public would get connected to the technology at an early stage, and also to integrate a hydrogen refueling station directly into the society by building it as a commercial station at a normal gasoline station. The difference between a diesel bus and a hydrogen bus is that the emission from a hydrogen fuel cell bus is nothing but water. So we are only getting clean, pure water from the fuel cell unit into the atmosphere. Hydrogen fuel cell vehicles will have almost twice the efficiency of a normal gasoline engine. So we're not only looking at different fuels, we're also looking at less emission and better efficiency. And then of course another major difference is that this bus is much quieter than a normal gasoline bus.
It's very good to drive. It's more quiet than the other buses. And also it looks good on the road and passengers like it, so it's really good.
The time frame of what we originally started with is almost on schedule, and we want to use the time from now until 2012 to prepare the society for the integration of commercialization of vehicles in Iceland, meaning we have to build more filling stations, etc., and get more experience from normal passenger vehicles. We're also aiming to participate in a marine demonstration as soon as possible, and the government still has full support of all our activities. They have actually changed legislation to make some incentives regarding taxation and etc. for hydrogen vehicles. So we are very happy with the progress, and we aim to see vehicles in the next few years in Iceland also.
I've seen the buses go around with a white smoke, and I think it's very good that they do that. The more hydraulic buses they have, the better, I think.
After a short ride on a hydrogen bus, we reach the headquarters of Icelandic New Energy to meet another key person involved in this ambitious project, the environmental manager, Maria Hilda Mack.
Environmental matters, they cross borders. And when you speak about energy, then I see 2 things. One is energy that is stationary, and one is an energy carrier, which we call usually fuel. Hydrogen is an energy carrier, and you can make it from all sorts of energy. But oil for example, is a fuel which you cannot make. Therefore, the question is about energy. How are you going to produce it and where is it? Then the answer is very simple. Energy is everywhere. But the economy of energy is more difficult in some places than in others. Up to now, governments have had much more support from economics than from environmental sciences. And I think the time has come that we have to shift this. If the whole world is at stake, then no economist can save us. But new technical solutions which are environmentally sound can. So it's simply a choice. And even though it is expensive right now, I am pretty sure that the world will gain from these types of experiments. So give us time and keep in mind that the oil economy has had 100 years to develop. Give us 10 to 15 years and you will have your solution for the same price, but a much cleaner world.
I think it's very positive, especially for the environment, and the leading role that Iceland has taken is, I think it's purely positive for us.
Very important.
Yeah, it is.
The great economic opportunities in history occur when we change our energy regimes and then we change our communication regimes to organize our new energy regimes. We are on the cusp of a new convergence. We've had this decentralized communication revolution in the last 10 years. Personal computers, the internet, the World Wide Web, satellite and wireless communication, and we've begun to connect the central nervous system of the human race. We've increased productivity, but there's a deeper mission here. What we're about to learn is that this new decentralized communication is the command and control to organize a new energy regime. We have to understand that a fuel cell powered by hydrogen and generated by renewable energy, we call it green hydrogen, a fuel cell powered by hydrogen is analogous to a personal computer. That's the key. If I have a personal computer, I can generate my own information. I'm my producer. The end user is the producer. Well, I have information I want to share with you. So I go up on the internet, and the web allows me to share it with 1 billion people. But the renewable energy future is not possible unless you have a way to store the energy. The sun isn't always shining. The wind isn't always blowing. Often there's drought, so there's no water going over the dam for hydroelectricity. So in good times, when all of that energy is materializing, you have to take some of the surplus, electrolyze water, and have stored hydrogen, and that's how you store your renewable energy.
The use of hydrogen to power vehicles, cars, and possibly even boats is intriguing, and one can see that most aspects of that have already really been worked out and are available today. Certainly improvements need to be made, but the most difficult part of getting this whole thing together is really storage and transport. How are we going to transport the hydrogen from the places where it's made to where it's being put into the cars? How are we going to store it in the cars? The problem is that hydrogen is a gas at normal conditions, and that means hydrogen takes a lot of space. Many different solutions are being suggested. No one really has a solution, I believe, today that is acceptable. For instance, the buses that are being used here in Reykjavik are using hydrogen gas at a very high pressure, 400 atmospheres. That's okay for cars that are coming in every night to their station and they're going to be refueled. For normal people, these would require too frequent refueling, and it takes up too much space. Liquid hydrogen is another solution that is being promoted by some people, but it has its problems. The volume is still very large. Many people are working on solid-state storage. Metal crystal, for instance, illustrated here with two kinds of atoms. It's a regular periodic array of metal atoms. It can soak in hydrogen atoms. Now the hydrogen gas would have to split up into atoms, and then the atoms will sit here in these holes in between the metal atoms. And the metal crystal is working then like a sponge that soaks up the hydrogen, and then one can essentially squeeze the sponge figuratively by heating it up, and it will release the gas again. Now the problem is that the sponges that have been used so far are too heavy. The goal now is to use lighter metals, magnesium, sodium, aluminum, and thereby improve the ratio of hydrogen to the total mass of the solid. We're working on magnesium-based alloys here. In my group, we do theoretical calculations on these things to search for the right alloy.
So you've been to Hannes and you've seen what Professor Hannes is doing theoretically. What we try to do is to synthesize the materials that he is calculating in this system. This is a magnetron sputtering system. We have these three magnetrons you can see here, and behind each of them is a metal or a material which we are trying to grow. We're trying combinations with magnesium and coal. The problem with magnesium is twofold. The kinetics is too slow. What we were trying to study was to increase the kinetics, or the speed in which hydrogen moves inside the sample. The targets look like this. Just a piece of material, very, very clean. The system is kept at a very low pressure. Then argon gas is let in. At a certain pressure of argon, we apply a voltage. Argon ions will get trapped in the magnetic field and they will hit the targets. That's why we call it a sputtering machine. It's like a woodpecker. One ion comes in, metal atoms come out. And then we have a fixed surface somewhere inside the chamber, and atoms rain on top of this surface. So this is what we call growing a sample. In this particular experiment, I'm growing layers of magnesium and then carbon. Magnesium, carbon, etc. And the only parameter that I change is the amount of carbon. I am going to start the growth. If you look inside, you can see like a blue glow, which is the plasma in front of this target. Now I've just opened the shutters. There are shutters in front of the targets. The shutters slide away for the amount of time that gives the right combination, and that's the way we control the thicknesses. I mean, we just open or close after what we want. You can see the resistance is going very, very fast down, which means that I've opened the shutter, and here I've closed it just to see if I have a conducting layer, and then when I've had the conducting layer, I open the shutter again, and then at this point, which is enlarged here, I put a little bit of oxygen inside, because if we have a sample of magnesium and you let hydrogen in, it will become magnesium hydride at the surface and no more hydrogen can go in. But if you put something like oxygen in a very small amount, then you break up this magnesium protective layer and more hydrogen can go into the sample, and this is seen by the higher resistance. Don't touch this for a while. Basically, they're just metal particles depositing on top of a silicon substrate, and I'm trying to grow 1,000 angstrom film, 400 nanometers, and the growth rate is 1 angstrom per second, so I just wait 4,000 seconds, and then that's done. The point where magnesium hydride starts to form gives us essentially the binding energy of hydrogen inside the magnesium. So at this point in pressure, for this temperature, magnesium hydride starts to form and the resistance goes up. 4, 3, 2, 1. Okay. This is essentially what it's all about. doesn't look like much. But this is just a piece of silicon. And then on either side, I don't really see which side it is, there's a very, very thin layer of, I don't know, magnesium or coal, I'm not sure. If everything works, 2 weeks of research can mean a half a year of just analyzing and interpreting in the right way and writing the articles and reviewing the articles and etc., etc., etc. So least of the time goes into the actual experiments. Most of the time goes into something completely different, but a necessary part nonetheless. This is just one of a huge amount of steps. We're working in storage. We are working under the assumption that we have hydrogen, but the production of hydrogen is maybe the largest problem. I mean, you don't want to produce hydrogen by burning coal, or I mean, you have to have, the ideal thing would be have renewable energies, which we have here in Iceland. But I mean, if we would have a material that we could store hydrogen in, how long until it's inside a car? I have no idea. I mean, there are probably years. But there's always this slight possibility to hit something that actually would work and would be a very good, very feasible material. And I mean, this is why we're doing it. Or at least why I'm in this. I would like to save the world, but I'm not sure I will.
So it's an enormous challenge. It's a challenge to chemists, physicists, material scientists. It takes an interdisciplinary effort, really. I'm convinced that with enough people working on this and enough effort put into this, a reasonably good hydrogen storage medium can be found. But it can well be that other options will in the end be better.
Iceland is a car nation and it's a big car nation and so, you know, you can't see it really in the near future, but hopefully, you know, in some amount of time we will have a hydrogen country. I mean, and people are pretty much aware of it and people are very positive about it, I think.
This building is the Technical Institute of Iceland. In this building there are done many researches. One of the subjects is energy, including hydrogen. I am doing my master's thesis here, trying to find a solution to produce hydrogen from hydrogen sulfide on geothermal areas here in Iceland.
We really need to break this up. And then this hydrogen could be put into a fuel cell or whatever.
We reached Professor Sigfusson and his students to learn more about other methods for extracting and storing hydrogen.
In the geothermal environment of Iceland, you have a lot of H2S and free hydrogen coming out of the ground. If you take, for example, a typical borehole in the north of Iceland in the Krafla area, you probably have up to about 50 tons of clean, if you like, H2 annually, and you also have H2S, which stems from the magma chamber on the ground, which Kristín Vala is studying now. And what we are working on now is a process to really not only abate the sulfur, but also harness the hydrogen. And what we are doing here at the Technological Institute, in cooperation with the energy companies, is to devise a method for making hydrogen and deposit the sulfur out of the H2S. What we have here is now a thermoelectric generator which converts the difference between the hot and cold water, if you like, into electricity. So we simply take in hot water, reduce its temperature a little bit, take out part of the heat and convert it into electricity. These thermoelectric electrons are then brought to an electrolyzer. It takes the water, splits it by electrolysis, takes the hydrogen, converts it again by taking oxygen from the atmosphere and returns the electron that originally was produced here. So what you have here is a little power plant, heat-based power plant, electron circuit, a PEM electrolyzer, water and hydrogen-powered fuel cell, which then powers the little motor here. I'll leave you to that when you talk to Halli. Let's go out and find the forest, Icelandic forest outside.
I'm a PhD student at the University of Iceland and I'm working in a project called Northstar where we are investigating potential for hydrogen storage. I am looking at ways to use metal hydrants to compress hydrogen. This is one process needed for the energy storage. What you're looking at here is a metal hydrate reactor, and we are using this reactor to compress hydrogen. And we are using hot and cold water, using the cold water to charge the reactor at a very low pressure, and we are using the hot water to discharge the reactor at much higher pressure. As you have seen here, we are trying to produce electricity, and then with the electricity producing hydrogen, and then we are going to use this device to compress the hydrogen for pressure vessels for later use with fuel cells or within the buses or whatever.
We are now in Iceland providing a basis for research and development and mostly for demonstrations. If we can, for example, like in the North Star project with geothermal compression of hydrogen, we can imagine that every house is its own energy master. That's a very fundamentally different situation from the oil cartel centers we live in at present.
We don't produce any oil, we have no fossil fuels, we have no gas in Iceland, but we have water and we have energy, but we also have the will to do it. And sometimes that's really the only thing that lacks. There are so many solutions to this fuel dilemma that you cannot implement in Iceland, but you could do in Italy or in Afghanistan or whatever.
Following Maria Mack's words, we went to visit an Italian entrepreneur who has invested heavily in hydrogen technologies. This man, who is no stranger to daunting challenges, is Adriano Marconetto.
Well, I think Iceland is a fantastic case history. Of course, there's a combination of culture, without which, even if you have gold next to you and you don't understand the importance of gold, you go nowhere. And then, of course, there's a huge availability of renewable sources. Is it easy to replicate that elsewhere? As we know, it's not easy. And again, I believe it's not easy exactly because of the lack of specific culture and sometimes lack of renewable sources. Iceland is very peculiar from that point of view, but it doesn't mean that you cannot take that road and run, you know. There are different sources, and there are, you know, they don't have the sun that we have, and so on. So there's a lot of opportunities in that field. At the beginning of the year 2000, I was working within the internet industry, and I was quite taken by the revolution that the internet brought into our lives. And little by little I realized that what the internet did for the telecommunications could have been done in the energy sector. The concept of distributed generation, the fact that everybody theoretically could be a subject able to self-produce its energy was quite interesting to me, and I decided to give it a chance. So we started a first company called Pianeta, which is Italian for planet, which was, and probably still is, the first Italian company focusing on what we call agile energy systems, small energy plants that can be located next to where the energy is needed. Working on that sector and seeing the company growing rapidly, we understood there was another big opportunity for us in our territory. Setting up a company, being able to design and manufacturing fuel cell power systems. So we set up electro-power systems in January 2005, and in less than a year we came out with the first prototypes of our power systems. One of these prototypes is now a product. We have a factory. A few months back we won the Italian prize for innovation, and we are ready to sell these products in Italy and outside of Italy. What excites me about the fuel cell is that you don't have anything moving or running or burning or whatever. It's noiseless, it's totally clean, it's very efficient, and can be a technology that can really give a strong contribution in changing our world. Hydrogen, chemical reaction inside, output is hot water, thermal power and electrical power. It's great, isn't it?
Try to imagine a billion fuel cells, just like we have a billion small computers. In 30 years from now, cheap, inexpensive. Every car, every truck, every bus is a power plant on wheels. You drive it during the day, you plug it into the grid at night. Every home, every industry, every industrial park, fuel cells powered by hydrogen, portables that people can carry with them. So try to imagine hundreds of millions of fuel cells where each person becomes their own energy producer, with locally generated renewable energy and hydrogen used to extract that energy. So, I'm going to have excess energy I don't need as a producer. What do? We're going to have to reconfigure every power grid in Europe and all over the world using the same architecture, the same software, the same hardware we developed in Silicon Valley for the internet. And we're going to reconfigure all those centralized power grids so they're decentralized, so that when I generate increased excess energy, I can send it back to a distributive web or a grid, peer-to-peer, and share it with others, just like we do information on the web. The coming together of distributive generation of information, the communication revolution, with distributive generation of hydrogen, and that is real power to the people. That is a great revolution in history. In my country, the White House announced they're for hydrogen, but they want to extract the hydrogen from coal or use nuclear power. That's using hydrogen as a Trojan horse to just keep the old energy industries in place. So the future is clear. We have to move to hydrogen. And also we have to be very clear that we're choosing green hydrogen based on renewable energy rather than black hydrogen based on coal and nuclear power.
Here you see an example of how to use the technology of using the fuel cell and electrolyzer. In this small car we have an electrolyzer and fuel cell, and we can use the sunlight to produce electricity, using the electrolyzer to produce hydrogen. We are making up some buffer of hydrogen in a tank, so it's now really fully charged, and then I can disconnect the car.
What actually is easy to get through to people are toys. All people like good stories and they like toys. It comes flat. And while people are just fondling this, fiddling with this, they can read all the instructions, and it's the only information that you need about hydrogen technology. You can have it in one picture on one sheet, and then people will understand what it means and how it works. That's all. It's a simple technology. There you have it, almost.
I know that hydrogen is good because gasoline is running out in the world, and I know that there's a bus here that is driven by hydrogen, but I don't know a lot about it. But they are teaching it in school also as well.
How to promote clean solutions, how to educate children, for example, and their parents through the children. This is, for example, an animated film, short film, which we have been sending to the schools. We often get school groups onto the buses, and then we teach them about this, and we often get groups of teachers. We can take them to the station and so on. I just see it that way, that I cannot educate the whole world. It's impossible. But as soon as they show interest, then it's their first step, and then it's much easier to follow up.
I haven't actually ridden one of the buses, but a friend of mine has, and they're supposedly quite quiet, which is both nice for the people in the city and the passengers. And I guess obviously the whole hope is obtaining some sort of sustainable goal for the future, and maybe that's what's going to happen here.
I think it's positive and very good, and probably it'll also be good for the Icelandic economy, or hopefully, if it means that, you know, it's something that we can sell and work from.
I'm really proud that it's happening right here in Iceland, you know, and I always feel so important when taking a hydrogen bus. It's, well, not many people can do that now, and I really think it's going to be big. I hope so.
I think the younger generation, this E generation, should start focusing. Yes, it's good to spend a lot of time on what you're against, but it's now time for the young people to focus their attention, take the responsibilities of leadership, and begin pressing to make sure that renewable energy is the future for their children and hydrogen power is the economy. The question now is, do we have the will and resolve to begin a massive global effort, leveraging public and private, the civil society, commerce, and government, and focus this as the main central priority of this younger generation on this planet. The major beneficiaries of this revolution will be the third world. The reason people are powerless in this world today is literal. They have no power, real power. 2/3 of the human race today have never made a phone call. 1/3 of the human race today has no access to electricity. The reason globalization has failed is it's top-down, based on an elite energy regime where only 20% of the human race has electricity, so they're the only ones that can produce and exchange with each other. 4/5 of the human race is marginalized or left out. If we can move to a third industrial revolution and provide cheap renewable energies and cheap fuel cells powered by hydrogen and a power grid that's decentralized, we have power to the people. It means the rest of the human race can have electricity. That means they can produce local and sell global. That means we can have deep exchange. Power to the people, real power. Ending poverty is making sure every person in the world can actually control energy and have access to it and use it to become a player in a re-globalization from the bottom up.
Iceland will continue to aim for hydrogen, but we need the world. We need the car producers, we need the fuel cell producers. We provide the platform, you provide the international technology, and with this combination I'm very hopeful that we will get closer to our complete hydrogen economy by 2050.
Iceland is a great test case because Iceland will show if it can be done there, it can be done anywhere.
Iceland is surely the most advanced country in terms of hydrogen research and development, but there is another noteworthy project being implemented by Hydro on the Norwegian coast, near Haugesund. This pilot project shows how wind power and hydrogen can provide all the energy a community needs to make it fully independent of fossil fuels. This is happening on the small windswept island of Utsira, the smallest of Norway's municipalities, with some 250 inhabitants. The first full-scale project of its kind in the world, it is a groundbreaking milestone in the development of green energy systems. We met Hydro's engineer, Torgeir Naken, on the ferry to the island.
Hydro has a long tradition in hydrogen, started almost 100 years ago, and we have continued making hydrogen solutions for the transport sector. We are developing and supplying hydrogen fueling stations. So we have delivered one at Reykjavik in Iceland, one in Berlin, in Hamburg. But it's not only done for transport, it's also for stationary power like here at Utsira. The reason why Utsira was chosen as our demonstration was because that, well, a little bit by accident, that at that time head of hydroelectrolyzer. He went fishing at Utsira and he met the local community councillor here, and they started talking about hydrogen, about wind energy, and the islanders had this strong ambition of exploiting the wind resources that they have, and the project was born. There are 2 wind turbines at Utsira, and together they produce enough energy to make Utsira self-sufficient, the total island. Well, this is the site. I'm going to take you through component by component, starting with the wind turbine and then take you through the plant. So let's go to the turbine. This is a turbine, has a capacity of 600 kilowatt, as I said. It's about 50 meters high. The diameter of the rotor blade is about 40 meters. So now you're inside the tower. So you can see here we are now producing 100 kilowatts, roughly the wind speed, 8 meters per second roughly. The power from this turbine is of course going directly to the customers when we have enough power, like today. Excess power we take to the electrolyzer, so we are not taking power to the electrolyzer, which is in this container. What you see here is you can see the stack inside the window here. In here you see the electrolyzer stack where power from wind turbine is used to split water into hydrogen and oxygen. Hydrogen is then dried and purified, we remove any oxygen, and it's taken to a compressor. A diaphragm compressor, 2 stages, which means it takes the pressure from 12 bars to 50 bars and then to 200 bars. After the compressor, the hydrogen goes to the hydrogen storage tanks. The hydrogen tank contains enough energy for 2 days of consumption without wind here at Utsira. From the hydrogen tank, the hydrogen goes to the fuel cell and the hydrogen engine. It's a PEM-type fuel cell. Capacity is 10 kilowatts. The engine is in that container, you can't see anything, but that's an ordinary diesel engine converted to run on pure hydrogen. The reason why we didn't choose the whole island for our experiments was obviously a cost issue, because if you should take the whole island, that would cost way too much. 10 households is enough to demonstrate that this works. The support in the island has been tremendous. They are very positive, very supportive of the project. It has been from day one actually. No complaints whatsoever about power delivery, power quality. So I haven't heard anything negative about the project.
Hello, come in.
My name is Jostein.
My name is Annie. This is my daughter Victoria, and I have a son as well, named Christopher.
We live in this house, and we take part in this project by Hydro. And they have been very clever to give us information on what this system means, and then there's no problem to say yes. So since then we have had our electricity from wind power and hydrogen power. We are very satisfied. We can't see any difference from what it was before, except in the beginning maybe there was a few times where we could see the light faded down but came back after a few seconds. But now the last year it's been perfect.
I think it's exciting because there's no pollution, and when you have children and going to grow up, you think about that.
There's a rubber band attached to it.
It's exciting. I don't think about it so much now because I'm used to it. But in the beginning I went there and looked at them, and it was exciting to know that we was part in the project.
This is the first project like this in the whole world, so that's why a lot of people come out here to visit the island, and that's good because it placed the island on the map. course, and that's good for us because we work in the tourist business, so it's very good for us. So of course we hope that the project will keep on after 2008, but also because it works very, very well. We have no problems in the house.
We like the windmills. You can't hear them in the beginning. Maybe they will make a sound that you can hear all the time, but you don't do that.
The demonstration started in 2004 and will run until 2008. That is the plan. So we are now midway in the demonstration. So far we are very satisfied, but what happens after 2008 is difficult to say. We are thinking about commercializing this product. That's the ultimate goal. But first we have to prove that this works. Of course we have to bring down cost as well. So we have to be competitive with mainly diesel generators. But if we can do that, we see that there is a market. We look for mainly remote areas in places of the world where they have renewable energy, obviously. You find them in the Mediterranean, in the Atlantic Ocean, Indonesia, all these places. It could be in China, Alaska, Siberia, and several places in the world. It will still take some time before the hydrogen society, as it's called, is developed. We are starting here. We are well on the way to demonstrate that this is actually possible. It will grow steadily, and maybe in 20, 30 years from now, hydrogen will be accepted in the society.
So I will see the first steps. My children, they will see the whole transformation, and when the grandchildren are grown, they will live in this new energy economy.
The 18th, 19th and 20th century were very much carbon-based, and I think that in the future this will be looked upon as a small glitch in history.
It's exactly the high-tech, clean, smart way of living.
We have found our way back to the second solar energy civilization, and at the end, so will also the rest of the world.
After this journey in the land of hydrogen, we return to Mr. Rifkin's opening sentence. Are we really close to the end of the oil era? This oil cemetery in the suburbs of Reykjavik seems to be telling us that we might be closer than we think. It could be a futuristic vision of a modern world that has abandoned oil for a cleaner, more sustainable environment. A society that has passed from oil to hydrogen. The choice is ours.